Hey guys, it's Miss Johnson and I'm here to bring you our fourth video for Unit 6. We're on Unit 6 Notes 4, which is exponential decay. So yesterday we talked about exponential growth, which is things going up or increasing. Today we're talking about exponential decay, which is things going down or decreasing. Our equations look very, very similar here. We have y is equal to c times 1 minus r to the t power. So again, that word decay means going down. And going down is the reason we subtract. So we're starting with 100% again. That value of 1 is like saying 100% of whatever we're starting with, but this time we're subtracting the rate, the decay rate, instead of adding the growth rate because we want to take it away so that it goes down. But all of those variables still mean the same thing. C is still your starting amount, R is still your rate of change. If it's a percent, you need to either make it a fraction or a decimal. T is still your time, which we sometimes call X. You know, same thing. And then also recognize that C is always that y-intercept where x is equal to 0. So let's take a look at just graphing some of these things. In number 1, I have C is equal to 16 and R is equal to 0.45. So if I write out a decay equation here, it looks like y equals 16 times 1 minus 0.45 all raised to the x power. So then I would want to slide this up a little bit. Then I would want to type these things in and give myself a table of values. I always use the same x values, -2, -1, 0, 1, 2, 3. And yes, I need to add a little row on mine. Yours has enough, but I'm gonna add a row. So when I plug it in, -2, it looks like this. Y equals 16 times 1 minus 0.45 raised to the -2 power. Type all that into your calculator. Be sure you use parentheses where you need them. I get a value of 52.9 there. When I type in -1, so same thing, but put a -1 in for your power. 16, 1 minus 0.45 to the -1 power, I get 29.1. Type in your 0, you get 16. Type in your 1, you get 8.8. Type in your 2, you get 4.84, oops, 84, and type in your 3, 2.66. So one thing to note here, our x values are increasing, but our y values are decreasing. And that's because this is decay. So y values going down means that I have a decay equation. So when I put these things on the graph, -252.9, that is way off my coordinate plane. I don't have that point on there, so I'm not going to be able to graph that point. -129 is even really high up, somewhere like up here. That 016 is really the first one that's kind of visible for us. 016 is back on my coordinate plane. 1, 8.8, now you can clearly see how it's going down as we go up, as we increase our x's. 2, 4.84 is down here. 3, 2.66 is 2 2/3, right about there. So this equation is coming down from way up there, somewhere that we can't see that's off our coordinate plane, and then curving. One thing to recognize, sorry, that was a bad line. Let me see if I can draw that again. Curving through these points, one thing to keep in mind is that as it curves, it's going to curve along the x-axis, but it's never going to cross the x-axis. This is still something that we don't touch. The x-axis is never crossed. So it will curve and flatten out here as it increases in x value. Let's take a look at number 2. Now I have a C value of 15, starting value of 15, and my growth, or actually, sorry, decay rate here is 1/3. So if I write out this equation, I have y equals 15 times 1 minus 1/3 raised to the x power. So that is put in my, that's my equation, that's my decay equation, then let's put in my x values, -2, -1, 0, 1, 2, 3. Um, when I type this into my calculator, this 1/3 is a fraction. It needs to go in its own set of parentheses. So this is one of those times that I have that double set. So open one set of parentheses, put your 1 minus, open another set of parentheses, and put the 1 divided by 3. Close that for the fraction, then close a second parenthesis for the whole 1 minus, and then raise it to the -2 power. And we use that little caret key in case you forgot. So when I type that in, I get 33.75. When I do that same thing for -1, I get 22.5. 0 is 15 because that's my y-intercept. 1 is 10. 2 is 6.67, and 3 is 4.44. So again, I kind of like to go out 2 decimal places and round accurately from there. Watch your rounding. Use those rules of rounding. If it's 5 and up, go up. If it's 4 under 5, 4 and down, stay down. That would be a point off on your quiz if you don't round properly. So -2 is positive 33.75. Again, way up here somewhere. Off my coordinate plane, can't see it. -1, 22.5. It's off my coordinate plane, but I can get there. There's 19, that'd be 20, 21, 22.5. So I'm a little bit off my coordinate plane, but I can still pretty much see it. 0 is 15, that's that y-intercept that we know about. 1 is 10. 2 is 6.67. 3 is 4.44. 4.5. So this one is curving a little bit more gradually. It's probably going to take a little bit longer for us to come down to that x-axis. But again, the point here is that it does curve to the x-axis, but never cross the x-axis. So be careful with that. And then it's going to go way up high in the sky there, way off our coordinate plane. So, all right, there's some graphing of exponential decay equations. Now let's do some writing of exponential decay equations. So on the back, it says a fully inflated raft loses 6.6% of its air every day. The raft originally contains 4,500 cubic inches of air. First part says write an equation to represent the loss of air using the general equation for decay, and then estimate how much air will be lost after 7 days. So let's go up to our top. This is my starting amount. This is my decay rate, but it's a percent, so I need to go back 2 places. That's 0.066. So if I wrote out an equation, I'd have y equals 4,500 times 1 minus 0.066 raised to the t power. Okay, so now this is representing the loss of air. This is going to give me the amount of air left. Air left in the tube, in the raft. Okay, so I need to be very careful with that in part B. So I can figure out how much air is left in the tube after 7 days, but I'm really looking for how much air is lost. So there's kind of a couple steps that I have to do here in B. One, I'm going to figure out how much air is left after 7 days. That's going to be my T. So Y equals 4,500 times 1 minus 0.066 raised to the 7th power. When I type that in, I get Y equals 27,900 and, or sorry, 2,790, 2,790.23 there. So then I need to take that and subtract, and when I take 4,005, because this is the air that's left. This is the air that's left after 7 days. 7 days. Okay, but I want the air lost, and that's just really a tricky wording in this question. So that tells me I need to take the 4,500 and subtract the air that's left, 2,790.23. So 4,500 minus 2,790.23 gave me 1,709.77 really. So 1,709.77 and this is in cubic inches, so inches cubed, that's how much air was lost from the raft. Okay, so we don't always have to do that second step. It just depends on the wording of the question. The wording in this question was pretty tricky because they want that air lost rather than the air that's left. So yeah, just keep that in mind. Number 4, during the past several years, the population of Campbell County, Kentucky has been decreasing at an average rate of 0.3% per year. In 2000, the population was 88,647. Write a decay equation that represents the population since 2000, and then assume this continues and find the population in 2013. So decreasing tells me that this is a decay equation, that key wording there. This 88,647, that's my C value. 0.3%, that's my R, but I need to go back 2 places, and it seems crazy because I have my decimal point in front of the 0.3, so it seems like I'm already there, but I'm not. The fact that there's a percent sign means I still need to move it. So this is 0.003. That's my decay rate. So my equation looks like this. Y equals 88,647 times 1 minus 0.003. And then I need to raise that to the t power, whatever that t is. Now we're looking for population in 2013. So I need to take 2013 and subtract 2000, which was the starting year, and I get 13 years. So really we're seeing the population after 13 years have passed. 647, 1 minus 0.003 raised to the 13th power. And when I typed that into my calculator, I got 85,251.31. We're talking about population, which is people. I can't have a fraction of a person, so I use the 3 to round the 1. That's 85,251 people. So really there were 2 answers in this question. The first answer was what's the equation? There's your standard equation given any year. And then the second answer was what's the population in 2013? And that was that right there. Number 5, during an economic recession, a charitable organization found that its donations dropped, keyword, by 1.1% per year. Before the recession, its donations were 390,000. Write a decay equation representing the charity's donations since then estimate the donations after 5 years. Okay, so I know that this is decay because it says dropped. My 390,000 is my starting amount. I didn't mean to write that again. I meant to write C. That's my starting amount. And then 1.1% is my growth rate. I need to take, since it has a percent sign, I need to go back 2 places, take the decimal back 2 places, so that's 0.011. So my standard equation looks like this. I'd have y equals, where did it go? 390,000. That's my starting amount, then 1 minus, because it's decay, 0.011 raised to the t power. That's my standard equation. Okay, so that's the first part. Then I want to estimate the population, or the donations after 5 years. So that's y equals 390,000. 1 minus 0.011 raised to the 5th power, and that gives me, I got, when I typed that into my calculator, 369,000, 016, sorry, that was a 369,016, 0.7376, that's what I got. This is money, so we're going to round it to the hundredths place, or in other words, the penny. Let me slide this over a little bit. Go back, get it all. There we go. Slide it over. You're still C. So if I round it to the nearest hundredths place, that means I want to look at the thousandths place to decide what to do with the hundredths place, and that tells me to round the 3 up to 4. So that's 369,000. 016, $16.74. We're talking about dollars, label it dollars, and there we are. Okay, so there's a few examples of writing exponential decay equations. Now let's just take a couple minutes to compare the difference between growth and decay equations themselves. So for numbers 6 through 10, we want to look at how do we determine whether it's growth or decay. So I'm going to slide these up a little. In number 16, you have y equals 7 to the x power minus 0.5. Now, here's the way you can determine. You need to look at the thing that's being raised to the x power. Okay, so look at the term with x as the power. So that means in number 16, I'm looking at this term. Okay, so 7 to the x power. Now, if it's growth, that means that your coefficient, or that b value, we talked about this back in unit and notes 2, b has to be greater than 1. If it's decay, that means b is less than or equal to 1, or I should say less than 1, but greater than or equal to 0. So between 0 and 1. So that's what I'm looking for. In this case, number 6, 7 to the x power, 7 is bigger than 1. So this is a growth equation, okay, because that was 7 is bigger than 1. In number 7, I'm looking at, it's hard to tell sometimes because we want to look at the 5 and say, oh yeah, that's going up, but that's just our initial amount. That has nothing to do with if it's growing or decaying. I really want to look at the term that has the x as the power, and 2/5 is between 0 and 1, so this is a decay question. In number 8, same thing. I'm looking at the term with the x as the power, and that is between 0 and 1, which means this is decaying or going down. Number 9, now I'm looking at 4 to the x. Again, I'm really ignoring the starting values. Starting value of 5, starting value of 2. Here the starting value was 1, or, well, and we're going down 0.5. Starting value of a half. I don't care so much about those if I want to determine growth and decay. I really care about the term that has the x as the power. So in number 9, 4 to the x, 4 is bigger than 1, so this is a growth question. And then in number 10, here's my term with x as the power. 5 is bigger than 1, so again, this is a growth question. All right, so that takes us to the end of our exponential decay notes. Thanks for listening. Check off your note sheet with Ms. Johnson and keep working on your practice assignments, and I will see you later.